So hello friends, in this video we have to learn about second order RL circuit. So how exactly this RL circuit uh, behaves when you connect this RL in series with a voltage source. So we know that when you connect with any source, voltage source, so there will be definitely a current. But what we are interested in is that how will be the shape of current. So this is why it is something known as a time domain analysis. So what it really means that we are interested in the shape of current as time progresses. So it may be like increasing in other case that we are going to discuss, in which you will find that current is decaying over a time. So which are the equations which governs the dynamics of those RL circuits that we need to understand. So let's that first part is when you will connect RL circuit with in series with a one voltage source. So at that time the current will increase gradually, and it will have some steady state value. So it will gradually increase and then it will reach to some steady state value. Okay, then this will is nothing but I0. So this you can just consider it as a V over R. And once you and this amount of current will flow when this switch S is and at position 1. Now in second case, when your switch is at position 2, so current will flow in the other ways. So it will look like it will start with I0 because initial current was I0, and then over a time it will decrease. Okay, so that we have to understand. So what are the dynamic equation that we need to understand. So firstly, when you connect with series RL circuit, so there is some voltage drop across VR, and similarly we have some voltage across VL. And if we apply KVL here, so we can write that V equal to VR plus VL. Now what is V? V is the source voltage. So this voltage get dropped across R and L. That's why I have written here V equal to VR plus VL. If you do not or if you have any confusion with this, you can just apply KVL here. So if I am traveling from here to here, voltage is increasing, so this is plus V, and then from here to here, plus to minus, so voltage is reducing, and again here also voltage is reducing. So the algebraic sum of voltages in a loop is equal to 0. So if you take these two terms on the other side, so this equation we can get. Alright, so this is V equal to VR. What is VR? So this is the voltage drop across a resistor, and this can be given as V equal to IR. And what is VL? Voltage across inductor. So voltage across inductor is nothing but L di by dt. Now if we divide this whole equation with R, so I am dividing with R in all side. So what I will have is L over R di over dt plus I is equal to V over R. And what will be the V over R? So this V over R is the final steady state current. Okay, so let's say this is L by R di by dt plus I equal to some initial current, which is I0. Now here if I further modify it, so L upon R di by dt is nothing but I0 minus I. Okay, so if I take this I0 minus I into denominator, so this will look like this: di upon I0 minus I is equal to L upon R into dt. Now if I take integration on both sides, so this is nothing but natural log of I0 minus I. Now here this integration with respect to di, so I have to differentiate I here, this entire term. So d by dt of I0 will gives me 0, minus di by dt will gives me minus 1, so minus 1. And here it is L upon R is the constant value, so it will be out of this equation. And the integration of dt, so I have to integrate from 0 to t. So integration of dt is t, and when I substitute upper and lower limit, I will get t plus some constant k. Now k is unknown here, so what will be the current when t equal to 0, when I am at the beginning? So at the beginning this I is 0 value, right? 0 ampere. So I is 0. So if I substitute this fact here, so what I will get is ln I0 upon minus 1 is equal to L upon R into 0 plus K. So K is equal to nothing but minus ln I0. Okay. So when I substitute K in this equation, minus ln I0 minus I is equal to L upon R into T plus ln into I0. When I take this term on the other side, this is ln I0 minus I minus ln I0 equal to L upon R into T. And if I this is only available when and one more thing is like this is negative here, right? So when I take this on the right left hand side, so this will become positive. This is minus ln I0 minus I, and this minus if I take on the other side, this will become positive, equal to L upon R into T. So if I take minus common on both sides, so this will be cancelled. So in short, what I will have is ln I0 minus I minus ln I0 is equal to minus L upon R into T. Okay, so this is the equation we will have. How we get this? So if I take common minus here, this plus will become negative here, and similarly and then if I take this minus on the other side, so I will get this equation. Okay, now the next step is to further simplify this. In equation we were having ln I0 minus I and plus then minus ln I0 equal to minus R by L into T. So this is in the negative, and so if I have positive here, so I have to multiply in ln. If I have negative here, I am talking about this position. If I have minus here, then it will goes in division. So L0 I0 minus I divided by I0 will be equal to minus R by L into T. So if I have log here, so if I take on the other side, so this is nothing but ln will becomes e raised to minus R by L into T upon I0. So thus it is equal to I0 minus I is equal to I0 e raised to minus R by L into T. So if I take this term on this side and this on this side, so I0 minus I0 e raised to minus R by L into T is equal to I. So I is nothing but I0 into 1 minus e raised to minus R by L into T. Analyze those things from this equation. What will be the current? So when t equal to infinite, my current I equal to I0 then 1 e raised to minus R upon L into T. And what is T? T is infinite. So this will become I0 then 1 minus e raised to minus infinite. So e raised to minus infinite is nothing but 0. So I equal to I0. And when what will be the current when t equal to 0? My current I equal to I0 1 e raised to minus 0. So e raised to 0 means 1. So I0 1 minus 1 will gives me 0. Thus if I plot it, this current I, so what is my current when time equal to 0? So when time equal to 0, the current is also 0, right? I equal to 0. And what is the current when t equal to infinite? So this is nothing but, let's say this is my I0. So the steady state value will be I0. and the in between what we have is the transient. Okay, so in this way our current will increase, and what it gives us this information. So this is nothing but time constant. So this tau is nothing but L upon R. 3.2% value it will reach within this tau timing. Alright. So this is all about when you connect any series RL circuit with a DC source.